It's a happy Friday. Hope everybody out there is doing well. Welcome. Thank you for attending this joint presentation of ISA Philadelphia and ISA Baltimore, Washington, D.C. section. This program is being recorded. I ask you kindly disconnect if you do not wish to be recorded. I'm going to put that note in the chat so everybody can see it. PDH credits are available for attending this meeting. I'm going to ask Tony from the ISA Philadelphia section if he'd kindly put his email in the chat with, if you want PDH credits, email me. Tony will help you with that if you need PDH credits. I ask turn off your cameras to avoid bandwidth unless you are presenting, and keep your microphones muted, please. We will share the presentation and the slides. If you give us about 72 hours after the end of this presentation, we'll post these to the ISA Connect website, and the video will be available on YouTube. I'll update the link in the chat to this meeting, so if you go back to the Teams meeting in a couple days, you'll find the link to the where everything's uploaded in the chat. Now I'd like to welcome we have Brian Ivy of ISA Philadelphia. Brian, if you wouldn't mind taking a minute and please share what you'd like to share.
Sure. Hey, everybody. Brian Ivy, the returning president of the Philadelphia section, here with our comrades from the Baltimore, Washington area to bring this presentation to you. Just real quick, I mean, ISA, and I know you're clicked in to look at PLCs and DCS, and ISA obviously is a big part of that process. But in terms of membership, I mean, a lot of people, you know, I think we're getting a little crosstalk in the background, but I guess you guys can still hear me. You know, on the internet, there's so much information out there, but it's really hard to discern what is the best information out there. So the one thing that the ISA does is it through ISA Connect, and I'll share my screen, it allows you to get some of the best thinkers in the industry to connect with them and to work problems out. You know, membership, this is not stuff that is available in the general Google search. These technical discussions are with the people that not only, you know, develop the technologies across the world, you know, because it's a worldwide organization, they develop the standards for the technology. So, you know, it's hard to get those people in a regular setting. In this way, with through membership, it's you're connected to them. The one thing that I was very pleased to see is some of you know, the younger engineers. I mean, these days with Teams and COVID, it's hard to connect. You're not in the office all the time. But I'll tell you, the ability for you know, getting more active with the boards, your local board, wherever you are in Philadelphia or New Jersey, Delaware, anywhere in the world, ISA has a geographic area where you can become a program chair. You can become the vice president of your area. You can become the president of your area, and age is not a restriction. So, I mean, I don't know too many organizations that will allow you to grow in your capabilities as a leader than the ISA. I took advantage of it, and I've seen others do it and benefit from it. And then, of course, the learning, you know, the standards and all that are available to our members at a discount. You can, of course, buy them as a non-member, but like I said, there's a lot of resources. And so anyway, that's the membership spiel. And if you have any other questions, please get a hold of me. You can Brian Ivy at verizon.net. We'll put that in the chat. But yeah, I think it's well worth your time. And the membership, it's isa.org. It's probably the easiest link you're gonna find. So thanks very much.
Thank you, Brian. Lloyd Risser, are you available for a brief introductory comments from Baltimore, Washington, D.C.?
Yes, sir. Yes, sir. I'd like to echo Brian's emphasis on the significance of the tool that you have, the ability to, at your fingertips, to talk to global experts in any topic in INC on ISA Connect. It's kind of something we've already had in ISA, but the ISA Connect brings it to your fingertips. Fantastic. To me, that's the biggest benefit of joining, just to echo what Brian said. But on behalf of the ISA Baltimore, Washington, D.C. section membership and board, I'd like to express our gratitude to the ISA Philadelphia section membership and board for the opportunity to co-host this event and future events. We look forward to continuing this what I feel is a mutually beneficial arrangement for a long time. That said, I'm really excited to hear this presentation. So that's all I had for today.
And let me
Cool.
just jump in real quick and acknowledge that our district, and I guess a real title is District Vice President for the Eastern North America, Colleen Goldsboro, is listening in as well. And she's actually a young technical expert. That I say young, I mean she's been doing it for years, but she certainly took advantage of the Wilmington section's hierarchy and moving through the vice president and president, and now she is she's the district vice president for Eastern North America. So again, she's a perfect example of this. And so Colleen's listening in as well.
Nice. Excellent. Thank you, Brian. Thank you, Lloyd. I'm Jeff Blair. I'm program chair of ISA Philadelphia section, Philly section. I'll put my contact information in the chat. If you are interested in becoming a guest speaker for ISA Philadelphia, we're always actively looking for programs, so we certainly welcome that. Today we will have questions and answers. I ask you please hold your questions until the end. Once our speakers have finished, we'll address questions as received in the chat. At that time, you may open up your microphones and cameras if desired. So opinions expressed today are those of our speakers and do not necessarily reflect the opinions of ISA Philly section. This presentation should be used for educational purposes only. And if you are joining us late, we are recording the session, just to be aware, this will be recorded and uploaded to YouTube and the ISA website. So now let me get to the good stuff. Please allow me to introduce our speakers today. We'll have Charlie Fialkowski. Charlie is a marketing manager, Siemens Process Automation and Instrumentation. He is a certified functional safety expert and has been a safety system specialist for more than 20 years with a focus on process safety. He served as chairman of ISA's safety division for both burner management systems and fire and gas systems, and is a former voting member of the ISA's technical committee, ISA 84, on safety systems. He has instructed ISA's BMS, LOPA, and SIS courses, published numerous papers on safety instrumentated systems, and recently developed ISA's course on burner management systems. Charlie holds a BSEE from Oklahoma State University. Also welcome Grant Kircher. Grant is an account manager at Thermo Systems, where he manages several key accounts and leads a group of sales engineers to support the business development team. After earning a Bachelor of Science in Mechanical Engineering from Drexel University, he joined Thermo Systems. He gained extensive knowledge in offering industrial control system solutions that increase efficiency and resiliency while reducing downtime and energy costs. Grant is passionate about providing automation solutions, offering low-risk, value-based options to meet the needs of the owner, engineer, and general contractor / construction manager. So allow me to introduce our first speaker today, Grant Kircher. Grant, the floor is yours.
Sorry, I was muted. Thanks for the introduction, Jeff.
Got it.
You can see my screen all right?
Looks good, sir.
All right, thank you. And if anything freezes, just let me know and I'll get that reset. But as Jeff had mentioned, my name is Grant Kircher. I'm an account manager for Thermo Systems, and we are an industrial systems integrator. And I'm going to be going over the PLC side of the discussion today. And I also want to introduce PLC Sidekick, the SCADA system, as they go hand in hand to give the complete package that we're able to compare to the DCS. So getting into it. So first is what is a PLC? So PLC stands for Programmable Logic Controller, and this is a customizable industrial controller used for automating processes. If we're looking at the actual hardware, the components that make up a PLC system would be the power supply, processing unit, an I/O interface to interface with the on the plant floor, the field instrumentation, the equipment, as well as a communication interface to interface with other PLCs, remote I/O interfaces, and the supervisory system. And then the next part is what is SCADA? So SCADA stands for Supervisory Control and Data Acquisition. And this is a term used to define the system of software and hardware elements that allow industrial organizations to control processes either local or at remote locations, monitor, gather, and process real-time data, directly interact with the devices such as sensors, valves, pumps, motors, using a HMI or human machine interface, and record events in a database. So some typical components that make up the SCADA system would be the actual application software, the databases, and the computer hardware such as servers and workstations. And I also want to mention the actual network infrastructure that ties the PLC, SCADA, and some of the equipment together. This is just made up of the switches and the physical infrastructure such as the cables and the configuration of that network. It's important to note that the PLC platform and the SCADA platform and some of the components that make up those systems, they can be from the same or different manufacturers. And they're typically integrated using a systems integrator such as Thermo Systems. So going back to a little bit of history on the PLC and its evolution over the years. So we have to step back about 60 years where PLC was introduced in the late 1960s. There's a long story about how they came to be, but it all started with a gentleman by the name of Dick Morley. And it's the man here in the left of the photo with the glasses. He's known as the father of PLC. And like I said, it's a long and interesting story. We don't have time to get into the full story now, but what him and his team came up with was called the Modular Digital Controller, or Modicon for short. That's a common PLC that we see nowadays that Schneider owns. It's changed hands over the years, but it was originally designed to replace relay logic systems to provide discrete control for manufacturing processes. Basically, the hardwired nature of the relay logic systems made it very difficult to make changes, troubleshoot, and keep up with documentation. And some of the components were mechanical in nature, and they would eventually wear out or simply fail. So the PLC was introduced to perform repetitive tasks in a reliable and durable manner. Some of the original specifications that Dick Morley had written down when he was thinking about designing a PLC where it had to have no interrupts for processing, it had to have direct mapping into memory, it had to operate slowly, which we'll find out is not the case today. PLCs are much faster. It needed to have a rugged design, which is still holds true today, and it needed to have an exclusive proprietary language, and they chose to use ladder logic to be very similar to the electrical schematics that were familiar with the relay logic systems. And we'll find out that's not the case today. It's a totally non-proprietary system. And then on the other side, the history of SCADA. So control, like supervisory control and monitoring of equipment was originally done the old-fashioned way. It was done using push buttons, analog dials, indication lights, chart recorders, some things we still see today, but just not to the extent as it was in the past. In the 1950s, computers were first developed and used for control purposes, and thus supervisory control became very popular among industrial markets. It wasn't until the mid-1970s where the actual term SCADA emerged, and this was with the rise of PLCs and just ways to increase monitoring and control of automated processes. Between then and today, the SCADA system has undergone substantial evolutions as it's leveraged new technology and strategies that have been introduced through that time. Some common applications for a PLC SCADA system. We typically see that in industries such as pharmaceuticals, energy and utilities, water, wastewater, automotive, food and beverage, oil and gas, chemical. And it's not limited to these industries either. In general, a PLC SCADA system is used in industrial applications that range from anywhere from a small or equipment level systems, and we're talking tens of I/O, like equipment skids, all the way to large and more distributed system. And this is thousands of I/O nowadays. We're talking about systems that are spread out over a campus, like utility plants, and just there's a great range in the size of applications that you can use, and then the applications itself. So I want to look at some sample configurations on a PLC SCADA system to give you a better idea of how the pieces play together. So the first one to the left, it's basically bare bones, minimum, very simple system that we have. So at the top, we have a PLC. We can assume that there's the I/O interface in the chassis, and that's going to be communicating and pulling the data from the devices on the plant floor, sending commands to valves, pumps, and then the SCADA server is going to be connected to the PLC. It's going to be pulling the data in real time from that PLC, from the devices on the plant floor. It's going to store that data in a database to be used for historical trending or whatever purposes you need it for, reporting. And then it's also going to host the application where it's going to show the HMI, where it's going to show the data in real time and have a means to access the information in that database. And that's going to be displayed on a SCADA client. Here we just have a single client, but then going into a more spread out architecture, spread out configuration, we look at the one to the right, where it's the same configuration, but now we're looking at remote I/O connected to the PLC. So it's a more distributed system that comes up to the PLC. That same PLC is then communicated with the SCADA server, where it's pulling its data and then again logging into the database, and then it's making the data available through the SCADA clients. And now here we have multiple SCADA clients that you can have in different locations, all in the same locations with multiple operators. It can kind of scale. Next configuration I wanted to look at was more of a redundant configuration. So again, it's the same configuration as we first started with, but now we're going to be building it out and put redundancy at different levels. So here we have redundancy at the PLC level, and the same amount of remote I/O that's distributed out at their facility, and it's going to be connected utilizing a fault-tolerant network, where if there's any break in the network infrastructure, they can still communicate with all of the I/O. If any of the either one of the PLCs were to go down, the other one's going to pick that up as a hot standby. That's communicated to redundant SCADA servers. That's going to be storing information in the same database. And then that's going to be communicated to, again, multiple SCADA clients that have access to both of those servers if one of them were to go down. And lastly, I wanted to show a very distributed and complex configuration. So here, this configuration, it has multiple sites that have multiple PLCs at each sites. Some of the sites have a local SCADA system that's communicating to a more central overlaid SCADA system. And it also shows the different means that it's communicating with those sites. Some are going to be their physical means. Some are going to be going through the internet and accessing it through the cloud. Also, the SCADA clients, how we're accessing that data on the front end. There's different means here. We have laptops, desktop workstations, a touchscreen, even mobile devices. So what this is to show you is really the scale and the capabilities of a PLC SCADA system. It's not just one size fits all. It can be smaller. It can be scaled to the size of the system or systems. And lastly, to round out my side of the presentation, I want to talk about the disadvantages and advantages. So start with the advantages. So PLC SCADA systems are rugged and reliable. Really talking about the PLC hardware here. They're designed to withstand high vibrations, high temperature environments, high humidity environments, and they generally have a very high mean time to failure. And for the SCADA hardware, we're talking about more computers, and depending on the grade, if it's more industrial grade, you can keep that in the suitable environment. But generally computers, you want to keep them in a suitable environment that is it's controlling the conditions. Next, it's flexible and customizable. So the PLC SCADA systems can be developed to be completely tailored to the specific application and customer requirements. So it's not just cookie cutter off the shelf. You get what you get. It's completely tailored to your needs. Also, the PLC platform and the SCADA platform don't have to be from the same manufacturer. This gives you increased flexibility and options with functionality. Next, it's non-proprietary. So the development software is widely available, and the programming languages are open source. So if you need support or if you need to make any modifications to your system, this can be done by even your internal staff that's trained up on the software, or by hundreds of local systems integrators. So you're really not locked into a single supplier. And also response time. Originally, it was specified to to operate slowly, but that's not the case today. PLCs are really ideal for equipment level control that needs to be acting fast. And it's also ideal for actions such as safety shutdowns and firing control. And lastly is cost. So PLC SCADA solutions are generally low cost and very proportional to the size of the application because of the scale that you can incorporate. And also just because it's non-proprietary and there's a number of integrators that can deploy these type of systems, it creates a very competitive marketplace. And then the disadvantages and some of the ways to combat these disadvantages is the first one is there's separate development and development environments and databases between as PLC and SCADA systems. They're separate. So this can lead to some compatibility issues. Also, increased risk for errors and mistakes. And the ways to combat this is, there's some additional development time, and really there needs to be a very robust factory acceptance testing phase to work out the kinks, work out the bugs before you get to site. Building on that, the components between a PLC and a SCADA system, they're typically designed and tested separately by the suppliers just because of the different number of combinations that are available. Some of the manufacturers, they do offer both a PLC and a SCADA solution, or they have their own family of products that work together. And Rockwell has the plant packs and all of their different platforms. Schneider has the EcoStruxure and all of those play nice together. But then you have some companies that are really just software based. You have Aviva with that was formerly Wonderware, or Inductive Automation with their Ignition platform. So there are many combinations. And again, to combat this, it's a little bit more development time and a robust factory acceptance phase to work out the kinks before you get to site. And lastly, there is a lack of redundancy out of the box. So redundancy isn't there at all levels right away. It's available. We have a redundancy that's available at the IO level, the controller level, the supervisory level, and the network. But these need to be designed and implemented in that way. It doesn't just come that way. And this adds to some development cost and deployment cost. And also, if you implement it a little later, it will end up costing more, and there could potentially lead to some downtime. Just some ways to combat this would to be make sure you're planning ahead. You're making the investments if this is something that's important to you, and just planning to scale. So really, what you want to do is just to try to get ahead of that. So with that closes out my end of the presentation. And Jeff, I'll let you take it from here. Thank you.
Cool. Grant, thank you. Appreciate it. And well done. And Grant will be available at the end of the presentation for a Q&A session. So now, Grant, thank you for that. I'd like to turn it over to Charles to continue the presentation, PLC versus DCS. What's the right technology? We are recording the program, so just so you're aware. And Charles, sir, welcome. We'll turn it over to you. You're on mute, sir. I think. Maybe everybody. For some reason, we can't hear you.
Quick mic check.
We're good. Gotcha.
All right. It's funny. I thought I took it off there, and unfortunately, I hadn't. So hold on one second. Okay, good. Well, again, Jeff, I want to thank you for inviting me to come be a part of this presentation. And Grant, it's been nice to work with you. I feel like after we had the initial discussion, maybe we should have titled this DCS versus SCADA, because I'm really going to focus on the DCS and the PLC technology at whole. So just a little bit background on myself. When I started in the industry, I worked for an EPC firm. We built utility boilers, large utility boilers. And when I first started working on P&ID drawings, I noticed that in the P&ID drawings, we had things called PLCs, and we had these flow indicating controllers over here. And I remember kind of nervously walking over to my mentor, and I said, what's the difference? I hear about PLCs, I hear about DCSs, and basically his quick synopsis was, well, a PLC does discrete control and the DCS does analog control. And that was my orientation into process automation at that time. So The other thing I could tell you is, if you look at this PNID, you can see that in this particular configuration, the PLC, which is indicated right here, is connected to this isolation or shutoff valve. So this is basically an on-off electrically actuated valve. Whereas on the DCS side, which is shown over here, it's connected to a temperature transmitter that then goes through a local temperature controller. So this has some type of display on it out into the field, and then it's digitally linked over into the DCS. The DCS is also, excuse me, bringing the information in from a flow transmitter, and it's doing some calculation to basically do a square root calculation, so temperature compensation for flow. So, you can see that there's a little bit more complexity along the DCS operation. Now, of course, someone would argue that nowadays this has gotten very, very gray. And again, back in the old days, you could physically tell the difference because generally speaking, this is what the PLC cabinet might have looked like. It was usually in some type of a box. Maybe it was in the control room. Maybe it was out into the field. There was usually a series of lights and push buttons on it, and maybe it even had a local HMI. Whereas the DCS was, kind of more this office-looking environment with a lot of monitors, a lot of information. So back then you could really tell whether you were looking physically at the DCS or you're looking at the PLC. Nowadays, it's getting more and more difficult to really see the difference. As Grant mentioned earlier, the basic terms when we talk about PLCs was a PLC and the SCADA. I'm going to throw a couple more terms here at you. In preparation for this presentation, I did dig around the web to learn a little bit about the history of the DCS technology. Well, basically because I'm not that old. But after a quick Google search, it was clear that the DCS history was really not as clear from what I could tell from the PLC. I mean, we heard about Dick Morley. It's very well known. 1969, he developed the first PLC. It was launched in the marketplace. When you think about the DCS, it was really primarily focused for the downstream oil and gas industry in the mid-1970s. Of course, there's a number of manufacturers out there that, quote, claim to be the very first one. So I'll let you guys decide who you think might be the first one. The other thing on the terminology, you can see that you hear the word DCS, distributed control system. There's process automation system, process control system, and this one down here, basic process control system. I can tell you one thing, if you ever get into any of the ISA or IEC standards, this is a term they're going to use instead of using the term DCS. So you'll see BPCS often, or you'll hear some of your colleagues even mention it as a BPCS. All right, a little quick history lesson. Basically, automation was used to eliminate manual control. So we started off with regulatory control being done by pneumatic controllers. One of the companies I was working for, More Products, was really a pinnacle company dealing with pneumatic controllers. In fact, these things may be 50, 60 years old and are still out there running today. They don't break down. They use basically air to move regulatory type of equipment. As Grant mentioned earlier, discrete controls was really done by relays initially. Single loop controllers soon came along and they replaced the old pneumatic controllers just because of their functionality, their ease of use, and their capabilities. And then, of course, we know that PLCs came along and they started replacing the relays back in the late 60s, early 70s. And then distributed control systems were now coming on board to replace those single loop controllers. So there's your quick history lesson of where we came from and where we're at. Now, if I had to compare the basic architectures, and this is a very simple drawing, if we start down at the field device level, typically the DCS and the PLC can handle the same and similar type of instrumentation down at the field level. But of course, some are more suited to handle more of the traditional analog heart type of signals versus some are more geared towards the motor control centers and the more discrete type of signals you might see. We showed and we talked a little bit about the I/O connections, and Grant mentioned too that the traditional PLC, it's pretty much built based on simplex. The concept of simplicity, or not simplicity, but non-redundant, whereas the DCS was really built inherently to tolerate failures. So you can see when you get up to the controller level on the DCS side, typically they will be redundant because no single point of failure shut down a process. We'll talk about that a little bit later. Then you get up to the HMI level, again, looking very similar on the DCS side compared to what we saw with the SCADA. You've got a set of servers here that are serving the data up to the HMI. And the difference is on the HMI level, you could have a single screen, you could have dozens of screens to hundreds of screens that could be scattered, within the same room or across the plant. There's really barely any limitations today. Whereas on the PLC side, typically it was done for local control, where you might have a local HMI on the cabinet itself and possibly a screen or two for just a simple HMI. Then the engineering environment, Grant mentioned, again, this is a little historical perspective because a lot of the stuff has changed over the course of the years, but historically the DCS was programmed in something we call function block design, whereas the PLC had started off in ladder logic. And then, of course, the networks, again, on the DCS side, inherently, these are all built based on redundant concepts. So everything that connects the signal from the field all the way up to the HMI, there shall be no single point of failure. Of course, you can minimize it and save some money by not going with redundancy, but the system was built based on redundancy versus the PLC side. It was built on simplex concepts or singular concepts, and they added on some redundancy concepts for those high availability requirements. All right, so that's a little bit about the overview. Again, kind of the challenge is physically they're looking very, very similar. They've got networks, they've got controllers, they've got HMIs. They can be single, dual, triple. They can have several levels of redundancy. And so you still might scratch your head and say, okay, so what's the difference? Now, if I switch back to the DCS discussion, I can tell you that the DCS was really designed for these, what we call critical continuous applications. You might see these in petrochemical, chemical, oil and gas and power, and there's other ones too. But these are the continuous applications where when you run this unit is going to be running 24/7, 365 for possibly 5 to 7 years until the next turnaround. So there are no opportunities to shut things down. On the other side, you have these complex batch applications, typically seen in the chemical, pharmaceutical, and food and beverage. And I say complex because this is where that crossover between, well, do I choose a PLC or do I need to go DCS? It really is going to depend on the complexity of the application. Oftentimes, we'll see, particularly in the pharmaceutical industry, maybe these units, these reactors might be controlled locally by a PLC and then supervised control with the DCS over top of it. So there's typically that type of mix, which brings me to my next slide. In some industries, both are really needed. So if you take the chemical industry, you can see there's need for DCS and there's need for PLC. Typically, the DCS is going to be running the reactors, the distillation, crystallization, fluid transportation, whereas the PLC will be managing possibly skid packages, packaging units, conveyors, those different type of controls that they might be responsible for. Same thing in oil and gas, food and beverage. You could go to pharmaceutical. You could talk about a lot of different industries where there's a need really, and you'll see these in the facility to have both DCS and PLCs. It's just they handle different parts of the facility. And what spun out of that is this idea of a hybrid. You can see here in the middle. So what we're seeing is you see on the left side is more heavily DCS responsible. On the right side of the industries that are more PLC based. And you can see there's a lot of in-betweens there. And that's something we call the hybrid space. And I can tell you, I don't know if some of you guys saw my LinkedIn video the other day, but I was showing the APAX and the quad log controllers. The APAX was really one of the very first hybrid systems out there that the company Moore Products developed back in the early to mid 1990s. The idea there was it wanted to do both control, traditional analog type of control, as well as being able to do cost effectively discrete control. Now, again, this is what throws a lot of confusion out there, but I could give you a simple analogy. It's kind of like the vehicles we choose to drive. I'm kind of a truck guy. I'm the weekend warrior. I'm running down to the local hardware and throwing some lumber in the back of the truck, maybe getting some dirt. And occasionally I got to throw a couple kids in the truck to take them to a ball game or whatever it might be. So you can tell the truck is more suited for that type. On the other side, you've got the person who wants the convenience of to be able to haul 7 or 8 people in a passenger minivan and, and still maybe haul a little bit of equipment, but they could you could definitely see where they had their strengths and different sides. And then of course, in the hybrid section is where we have these new things we call the SUVs, where they're built on a truck base so they can handle some heavy loads. Plus they've got a lot of comfortable space for, a large family to drive in. So I consider the SUV type kind of the hybrid in the industry, where again, they can all do pretty much what you're looking to get them to do, just some are better suited to the other. But of course, then you're always going to have that one guy who takes it to an extreme. So this person decided he wanted a passenger van with the ability to haul a lot of equipment. So of course, and I always say that whenever I talk to an engineer who has a control system, he can make it do whatever you want it to do. There's no doubt about that. And I talked about the optimization. So if you look at this chart here, where we're looking on where the DCS is really optimized for versus the PLC, the different modes of control. So when you're looking at strictly continuous control, batch control, process safety, it's more inherent to the DCS. Then you start getting that overlap with the high-speed logic on the PLC, the machine safety, and the motion control. Let me give you another example. Several years ago, I was attending an SIS, a Safety Instrumented System training module, where there was a few customers from a refinery in the Gulf Coast. The instructor was from a PLC manufacturer, but he had this system that was safety certified, and he was trying to creep into the process safety business. So, of course, there's a lot of overlap. The customer kept peppering him with the peppering the instructor with examples of failures, like a wire break. What does the system do if there's a wire break? What about a communication failure or a CPU fault? So he kept peppering him with these concerns that he had, and the instructor just kept proudly saying, no worries, if anything happens, we will just shut you down. Because that is, again, how the system is certified. It's going to fail safe. And he felt pretty competent and confident that that was the right answer to give. And after about the 3rd or 4th time, this customer who I didn't really know, leaned over to me and he goes, I work at a refinery. And he goes, we never shut down. So you can definitely tell that while the system this one particular manufacturer was demonstrating, it was not well suited for the continuous process control. Of course, then there's other topics that people might consider to determine which technology might be best suited for their decision. What type of product they're manufacturing, what are the downtime costs, what about the engineering expectations? Are you going to engineer it locally, or are you going to use a local system integrator, or are you going to have the manufacturer do the engineering? How do you maintain it? What about performance requirements? So there's a lot of different things here. We'll take a look at those here in the next couple slides. So the first thing I would say is, what is being made? What are you manufacturing? What's the product? What's the process? And what's the value of that material? So again, on the left side, on the DCS side, normally we're talking about raw material transformation. So it's refining, it's separating, it's blending, it's reacting. Those are the typical manufacturing process. On the right side, more PLC based, or more of the manufacturing or assembly lines, bolting parts together, things like that, very discrete. The other thing is your process visible while it's in mid-process? Typical on the DCS, you don't see the process. It's within tanks, piping. You just don't see the process. Where on the PLC side, the products are always, or generally speaking, they're typically very visible during the mid-process. So here you can see an example of a bottling plant. The other thing is, what's the value of the product you're manufacturing? On the DCS side, it's usually something of very high, very critical value. Take, for example, there's a pharmaceutical plant we're working with where one batch will cost over $1 million. So they cannot afford to mess up that batch application. So they've got to be very considerate about that. Versus on the PLC side, typically lower individual value. On the DCS side, as far as downtime, downtime can be dangerous or even damaging that product. You take the example of a refinery, if they shut down that refinery, they're talking hundreds of thousands of dollars per hour of them being down. And when the refinery goes down, it's not something you can just flip a switch and get back up online. It takes days to get that back up and running. Whereas on the PLC application, it's more downtime usually only results in a little bit of lost production. Normally if something fails, you can get it to repair it in time and then flip the switch and get that bottling plant back up and running. So that's just one example of it, and helps you make the decision on what's important to you is what is being manufactured. The other one is how's a plant being operated? On the DCS side, normally the HMI is located in a central control room. The plant is operated by the controllers as well as the HMI. Sometimes there's sequences and things like that the operator has to interject and has to go in and maybe trend something up as they heating up the process or whatever they're doing. So the operator is very involved in that process. As well as the operator needs to get a lot of detailed information as far as alarms. Maybe there's remedies on taking the next step. Maybe he needs to get that diagnostic information when a valve is starting to fail. Maybe he's losing a little bit of control. So the operator has to really work very close in hand with that HMI, and he's not right there at the process. Typically on the PLC side, the machines may or may not need local screens. It just depends. The controller logic itself is really what operates the plant. There's not usually a lot of interaction from the operator. So it's not really necessary. And generally speaking, the HMI screens are giving him limited information, just enough that he can run and operate the plant. If there is a fault, he might get a quick indication of a fault, but he probably wouldn't be able to dive down and find out exactly where that failure had come from within the plant. Again, because it's probably more unit-based type of control. And again, I'm speaking in very general terms. I'm sure Grant could sit there and go, no, we could do all that. We could do all that. And I'm certain that a PLC manufacturer can, but it's not designed that way right out of the box. So it's got to be configured as opposed to just being developed that way. As far as the system performance requirements goes, on the DCS side, we're not typically as worried about the high-speed requirements. So we're typically at the 100 millisecond to 1 second operation, whereas a logic scan for a PLC might be less than 20 milliseconds. So they're very quick. I mentioned before about the redundancy requirements. DCS often requires redundancy, as well as the ability to make online configuration changes. Again, we can't stop the process. So if we need to make a change because maybe one of the triplicated transmitters had failed out in the field, you've got to replace it, but maybe it's a different type of technology. You need to go back and adjust the configuration to accept that new device while you're online. And again, I mentioned before, it's really based on having the advantage of dealing with lots and lots of more analog type of control. Whereas, again, on the PLC side, simplex is typically fine. Offline changes aren't really a necessity, and they can do analog control, of course, but they don't have a huge amount of typical operation for analog control. And then you get down to the engineering side. What are your engineering needs? On the DCS side, you basically are getting a block, a library of tested and certified and standardized function blocks. These are the configurations that you would drop down on the screen that do specific functions. For example, let's say it's a time delay function, or let's say it's a voting function, or whatever it might be. These have all been pre-developed, pre-canned, and you're just dropping them down on a screen. On the PLC side, typically it would require some customized coding. I was talking to one of the PLC manufacturers. We were comparing notes, and I was showing him this mid-select block that we had on the DCS side, where you can bring 3 transmitters in, and it automatically selects the mid signal, And if one of the transmitters goes out, it readjusts, and it just makes sure that it gives you the most confidence that you're getting the right process signal, process variable into the control system. Whereas on the PLC side, he goes, yeah, we can do that too, but not out of the box. So they could build that logic, they could build that functionality, but it's all going to be customized. The other thing is when you're dropping on the DCS side, when you're putting your DCS code together, you also get along with that because of the common database we exploit, the ability to build these HMI graphics. So when you drop down a control valve operation in the DCS, some little block that is going to basically run that control valve, you also get an HMI element along with that. So your HMI screens are starting to be built with that intelligence. So so now from the engineering side, you're dropping down that control valve or motor valve block or whatever. On the HMI side, you also get a little block icon that will come along with that, that's automatically tied to that function in the controller. And so now when you're on the HMI side, all you have to do is click on that, and that'll open up a pre-designed faceplate where you have all the information available for that particular process or automation or function. And again, on the PLC side, typically not required, so they have more, generally simpler, customized HMI graphics if even necessary. The other thing on the DCS side is everything is all tested before startup. So if you could have multiple controllers, multiple servers, multiple OS stations or HMIs, and everything has to work in harmony before you can even go to startup. That's why we have something we call a factory acceptance test, which is really testing all that information is working in sync together. Whereas on the PLC side, typically it's not a requirement, as they're more unit-based control. They test their single function at that particular area. And, they worry about the integration later on when they put them out into the plant. Then they can tie all that information together and share data and do whatever they have to do. And again, it's more customized at that point in time. And finally, I wanted to just touch on, again, both systems have advantages. I think Grant talked about the advantages and disadvantages. I would say on the DCS side, the advantages are the single global database. So no matter how small or how large that system grows, all that data is available throughout the entire system. Take, for example, one of the early plants I ever worked on, we were using a hybrid system, and we had 5 operator screens, different stations. And if one operator acknowledged an alarm on one screen, the other screens didn't know that alarm was acknowledged. So we had to go in there and tie that together manually. On a single global database, if you have 30, 40, it doesn't matter how many screens in different building units or whatever, if one screen acknowledges that alarm, all the other screens will recognize that alarm has been acknowledged. The operator empowerment and insights. So again, the DCS handling more information, it provides and reduces the need for engineering interference. So once the unit is up and running, it gives the operator really a lot of availability to adjust set points and do things without having to really call in the engineering group to do any reprogramming. Again, I mentioned it can manage complex controls such as batch. It has typically advanced functions. We've been talking a little bit about alarming, asset management, even integrated safety. And again, extensive libraries and pre-built graphic elements I mentioned before. And when I talk about libraries, it depends on, there's different libraries for different industries. I know from Siemens' perspective, we have a library for the sugar industry. We have a library for the chemical industry. So we have different libraries that are really built for those different types of industries and applications. As far as advantages of PLCs, the nice thing about they have and handle a very low-cost local HMI visualization. And I can tell you on the DCS side, we can have a local HMI, but it's not going to be cheap and it's not going to be easy. They're just not built that way. Normally, because that little local HMI doesn't really talk to 2 different PLCs, it's a very simplex communication. So you've got to engineer a solution around that. We've done it before, but it's not easy. So the advantage for the PLC is a local HMI. It's typically more compact, low cost. Give you a simple example: a DCS controller might cost you anywhere between $10,000 to $40,000, whereas a PLC might cost you $1,000. They're typically preferred by package or skid OEMs. Again, that's because they're compact and low cost. They definitely handle high-speed applications much better, and they are simple to program for basic functions. So simple functions they're really built to easily handle that, and without much complexity or much experience, even what Grant mentioned earlier. So that's what I had. I wanted to just thank you guys again for your time. Hopefully this is well worth it. I know we're going to open up for questions here. I wanted to share with you that, here's our contact information for both Grant and myself. We also have our LinkedIn. So if you take your phone, you want to connect via LinkedIn, you can scan our QR codes there and get right to our LinkedIn profile page, and I'd be happy to connect with you. The other thing I'm working on is I'm working on finalizing a new white paper on this very topic. And this is what kind of inspired me when I first got contacted by Jeff. I'm hoping to have it done in the next couple months, but this is really going to kind of walk you through some of the decisions and kind of checklists on whether you should be more geared to or looking more of a PLC as well as a DCS. So if you'd like to get a copy of it, shoot me an email, and once I get it published, I'll be happy to send it over to you. So Jeff, with that, I'd like to, again, we can open it up for questions now.
Cool. Thank you. Well, Charlie, we'll give you a minute to catch your breath. It's not easy to talk to, you don't know how people are reacting. It's different presenting online than being in front of a live audience.
I know, right?
And if you want to take a minute to catch a drink or something like that, I can tap dance for just a minute or two.
I'm good.
Hey, Charlie,
But in all seriousness, we want to thank Grant and Charlie. They're going to be proud owners of an ISA Philadelphia presenter coffee mug. So if you want to be as cool as Grant and Charlie, I do encourage you to I put my email in the chat there.
Hey, Jeff, I would prefer the hat you wear, because my brother in the Midwest sent me this hat. So this is all I got going on right now.
Oh, there we go.
You're not going to tell everybody you were over at my house last weekend watching the Eagles game, right?
No.
We'll keep that on the down low. All right, all good. So with that being said, it is time for Q&A. We have one question in the chat. So before we get started with that, just let me put out a couple of things. So like I said, the opinions expressed are those of our speakers today. And if you're reading, ISA Intech, you're talking to vendors and things like that, you'll hear things about PLC does this, DCS does this, we can do everything. And I've been exposed to that. You walk the trade shows, you talk to vendors, there is some overlap in there for sure. There's things like cloud connectivity, cybersecurity, all these different topics that we could address. So in a 1 hour time today, thank you, gentlemen, for both meeting the goal and getting a great presentation out. We will put this online and record it. So that being said, I'm going to stroll through the chat, and but we had one question typed in during the meeting from Hein Pham. I don't know if he's still online. Let's see. He asked, we have several, and I will go ahead and open up the microphone. So if we get some background noise, we might mute you, but you should be able to open up your microphone now, Hein. We have several machine package controlled by PLCs. However, the vendor put in the password protection, and we're not allowed to access the PLC code. What are your opinions about that?
I guess I could take that one. So like I had mentioned, the programming language is non-proprietary. So I mean, anybody can get into it and make changes, with the caveat that if someone puts a password on it, you need to know that password to get into it. So I don't have any real backdoor options to get into anything to hack your program. So I don't think there's anything to really help you out with at the moment, except for getting in contact with that vendor to see if they're able to provide you that password or provide you with the program without the password. I mean, they may have done it for safety reasons because it's equipment level control. They don't want to be liable for someone going in making changes and then it causes a safety issue. Or maybe they were trying to lock you into just using them. So there's reasons there, but I think up front you can consider this when selecting a specific vendor if they are going to lock you down with the password. Also, you can put it in your requirements to them when you're sending out your RFPs and just say, hey, we don't want anything that's going to be password protected, or we want to have this password that when you turn over the package. So, I think that should cover it. Does that answer your question?
Yes, you did. Thank you so much.
You're welcome. Thanks for the
Yeah.
question.
I have another question, if you don't mind,
Go ahead.
about the DCS system. PLC, I know very well that it can be do the motion control, but I did not see on the DCS side. Can it do the motion control? Thank
No,
you.
and again, that's again, sure it could do motion control, but it's not what it's designed to do. If you had to do strictly motion control, I think the PLC is going to be a better fit for you.
Okay, thank you.
Yeah, appreciate that. It's again, you know, they do have, there's certain things they're better at than others. So
Yeah, and usually because motion control requires extremely fast response times. So.
okay. Jeff Stoss.
Can I ask one more question, please?
Go ahead.
Because he mentioned that it's require extremely response time. When you say extremely response time, what are we talking about millisecond, microsecond, or what are we talking about?
Again, it just depends. You know, I can tell you right now that our DCS happens to be very fast responsive, but what happens is it eats up a lot of the memory. So normally, you know, the faster you want some of the components to go, I don't say limited, but you just don't want to put them all in there. It's kind of like if we all turned our cameras on, the bandwidth of this recording will probably shut down. Okay, so we've got 3 cameras on and we're okay with this. So on the DCS side, if you had, let's say, a handful of loops that you do really fast control, you could do that. But generally speaking, on the DCS side, control are somewhere between 1 to 3 seconds. You know, we don't, you know, you've got a lot of inertia in a process control environment where it's going to take a long time for something to fill up or something to heat up or cool down. So we don't need to run it in milliseconds. We can run it in seconds. And that's really what the DCS was designed to do. But of course, on some airflow loops and things like that, we need to be a little faster. We do have some areas in the DCS that we can run some faster control loops because we need that functionality and capability.
Good stuff. Thank you, Charlie. So Jeff Stoss has our next question. It's talking about the line being blurry and possibly a, you know, looking at the cost. He says, curious on thoughts about when the cost of the DCS is worthwhile to implement at a facility over a PLC system. Given PLCs now have redundancy, implement P&IDs and cascade P&IDs and scale the I/O, the line is blurry, and a DCS package is quite a jump in cost at this time. From Jeff Stoss. So either of you want to take a first crack at that, or I mean, I know you both have opinions, so we can welcome them both.
I can start.
Sure, Grant, go ahead.
Yeah, so I think, yeah, there's obviously a difference in cost between a DCS and a PLC system, and I think, you know, over the years we've seen the bridge between the two in terms of functionality start to close. So I think you need to look at, you know, your application. Does the functionality of each system, does that meet your needs? Does the performance meet your needs? If the answer is yes for both of them, then you just need to, I think, ask yourself, you know, what's important to you? Is it cost? Is it the support structure? Is it could be a number of things, but I think you need to look at like what the considerations are and why you would be making that jump. And one of those is cost.
Sure.
Yeah, and you know, back to what we talked a little bit earlier today, a lot of it is your requirements. You know, with on the PLC side, because that HMI is built for that application at today. If you make changes later on down the road, you're going to have to get an engineer to make those changes, correct that HMI, you know, work on the system more. So as you're moving and progressing in the design of the system, now, of course, you say, hey, we're going to build it today. We're not going to touch it for 5, 10, 15, 20 years, whatever it might be. It's just going to really depend on what your needs are. And what your applications are. And whether it's worth it or not. You might pay a little bit more up front for the DCS, but because of the functionality of the libraries that are there, you don't have to engineer all that from scratch. You'll spend less time engineering it, so your engineering costs might go down to actually build that system. Whereas on the PLC, it's more customized, so it's going to take more engineering time to build that application. But if the application is real simple and basic and straightforward, then it may be a moot point. So it just depends.
Okay, Jeff, I don't know if you want to chime in or if you want to open up your mic, you're welcome to. If you want to, did that answer your question, sir? Okay, yep, Jeff's good to go. Thanks, guys. So we queued up Grant for he got the first crack at the last one. So this next question will turn to Charlie first. This comes from Luis Manuel Garcia. He says some DCS can execute PLC routines by manipulating execution times independently. This is thanks to very fast processing capabilities, yet enjoy one single database. Is this what you mean by hybrid?
Yeah, I mean, the hybrid normally,
if you want to take a crack at redefining hybrid or maybe recircle back to that, Charlie, kind of what that encompasses. And I've heard that term a lot in the industry. It's a hybrid system and things like that.
well, I think what you're seeing is all the systems that we look at today.
I'm not sure how the reply's got file right now.
Hang on, we got an open mic here somewhere. I'll find it. There we go. I think we got him muted. Okay.
Actually, if Luis wants to take his mic off of mute and ask that question, because I don't really understand the question.
Luis, you out there? We see you.
Yeah.
Okay, go ahead, sir.
Can you hear me?
Yeah.
In some DCSs have very fast processors, and they allow you to do some routine with one speed and another routine with a different speed. It's kind of having a PLC inside a DCS, right? And yet it's a single point of entrance for your database. So I wonder if that what you classify that as differently, or you call that a hybrid?
I didn't classify that. I would say that's just a different technology being deployed by a certain manufacturer. Simply put, if you think about the way a PLC runs code, and when I say PLC, I'm using let's say a controller. And Grant, maybe you could back me up on this. It normally reads from the controller code from like left to right. So and the less material in there, the faster it's going to be able to execute. What Luis is saying is there are PLCs or DCS, whatever you want to call them. There's controllers today that you can take and segregate the code in different areas. Okay. And so if you had a little bit of code that needed a really fast response time, you put that in this one section and it's running very quickly. And then you could take this other code, which might be longer and less concerned about speed, and put it in a different section of the controller, and it runs at a little slower rate. So, it's running a little bit different, but I don't consider that hybrid, because when I look at again, I'll say the old APAC system that, more products came up with was considered a hybrid. It had two different databases. Okay. They took a Wonderware HMI and they engineered the HMI from the manufacturer to look like a DCS. So it had the navigation, the alarm management. It put a lot of that DCS functionality on top of, the PLC body. The engineering of it was all based on function blocks and ladder logic and all that. So it looked like a PLC, smelled like a PLC, but acted like a DCS. And that's what I mean by hybrid. Because again, that area is becoming grayer and grayer. It is more difficult to really look at a box and say that's a PLC or that's a DCS. You can't even tell physically anymore. And now with the SCADA systems, that DCS screen that I showed earlier, where it had all those screens up there, that could have looked like one of Grant's SCADA systems. So you can't tell.
And Charlie, to your point, I saw a LinkedIn video from you today on your LinkedIn page where you were holding up the card from a DCS and a PLC, and it's like,
they're the same.
Could tell the difference.
Yeah.
I mean, so Yeah.
Yeah, and I also want to add on to that.
Yeah, please.
Not really add, I'm actually looking ahead in the chat and some of the questions, and I saw one that said, can you talk about integrating PLC systems with the DCS? So, sometimes, and we've actually had some examples of, we have customers that have a DCS for their site, and they have this system and they want to implement a PLC system there and integrate it to the front end of the DCS. So it's fully capable of doing that. Depending on the type of control, if it's the response time, if it's the support, if it's just the functionality or familiarity with the PLC controller, we've implemented that and then just integrated that with the DCS. We made the data available through some sort of communication protocol, Ethernet, whatever it may be, and then have the DCS vendor. They do the work on their end, pull in the data, and we'll make that handshake and they display it. So we can definitely integrate them. I don't know if it's the ideal, but you can certainly do that.
Yeah, there's a new terminology coming out in the industry called MTP, or module type package. And basically what that's going to do is take a PLC take a skid or package unit manufacturer. He buys one of Grant's PLCs and puts it under the hood, implements it for his little application, and then the DCS, which is called the orchestration layer on top, can import that code into the DCS, and now that basically looks like it's part of the DCS with the face plates and the block icons and the alarming and all that HMI elements and stuff like that. Instead of mapping all the data, it's now basically sucking in the data from a single module MTP package, it's called. This standard is just being issued, and it's been issued now for a while, the first test of it, or first release of it. And this is something that we're very excited about in the industry, because it's going to simplify integration of PLCs and the DCSs. In the old days, you had to map everything manually.
So that was Stan Hilton's question. Stan, did we answer your question for you? Awesome. Okay, good deal. We're going to skip, looking a little bit backwards. Somebody who's after my own heart here asking about field devices. On the field device end, are the inputs and outputs the same? For example, 4 to 20 milliamp and 120, or are there dedicated field devices that are compatible with PLCs and field devices with DCS? That's from Dave Oler.
Yeah. So if you take a field, when you say field devices, let's take a simple one. Let's take a pressure transmitter. Okay. A conventional pressure transmitter. There's a whole host of pressure transmitters that are out there, from Anderson Hauser, Emerson, Honeywell, Siemens, Yokogawa, ABB, etc. So and I can tell you from the DCS side, I don't care what transmitter it is. It just has to be giving me a signal that's defined in the 4 to 20 milliamp /heart space, and we can just plug that in and bring that information in. So that doesn't matter. Normally, though, the DCS will have an I/O card that has maybe 12, 24, 32 channels it can bring in one card. The PLC will have an analog input card that could do the same thing, but it might be 4 channels or 8 channels, because it doesn't have to handle so many. Yeah, you can bring it in, but you might, and now if you got hundreds or thousands of pressure transmitters, you can see the DCS probably can get that job done in a dozen analog input cards. The PLC might need a couple racks to do that. So hopefully that answers your question. Now, I will tell you on the flip side, when you talk about 120 volt AC, these are for discrete signals. So this is a limit switch that we want to see if a valve has been opened or closed. And you got lots of them. Every valve has an open limit switch, a closed limit switch, maybe a mid, somewhere in between limit switch. So now you've got 3 limit switches per valve. You want the cheapest way to bring that information in. And historically here in the US, that's been 120 volt AC. I can tell you right now on the DCS side, we can do that. We're just not real good at doing it because it's, again, more costly. We have the ability to do that, but it's just we can't do it conveniently and as cost effectively as the PLC can do it. It's just the inherent nature of the base systems. So And that's kind of that gray area. You know, you go talk to a PLC manufacturer, we can do analog in, we can do analog out, we can do discretes in and out. And you talk to the DCS guy, he can do the same thing. But, you know, then you got to look at what's the price per signal and start maybe evaluating it that way. If it's more analog intensive, the DCS is going to be cheaper. If it's more discrete, the PLC is going to be cheaper. So that's why it's all part of that. You know, you've got to understand, you got to talk to the vendors and understand the technology and, you know, start kind of comparing apples to apples there.
And actually, that topic may make a good program someday, the interoperability and, you know, integrating field devices and instruments. And, you know, it's one of the big topics in ISA, you know, certainly. Grant, any thoughts on that?
Yeah, I agree with just about everything that Charles said. I mean, the field devices, if we're talking about the I/O interfaces for a PLC system, yeah, as long as it's 4 to 20, 0 to 10 volts, you know, the digital singles, obviously we could take them in. There's I/O cards for that. I don't think there's any like proprietary interfaces that like a field device would use. I think that would not be in their best interest. So I think keeping it flexible so you can go with the DCS or PLC, it's the same devices. So
Yeah, and we see open architecture kind of reigning the day. I'm sure we all remember back in the day when the instrument manufacturers, you know, was the same as the DCS manufacturer, and they had their own proprietary protocols. I won't mention any names, but you know, it kind of went to 4 to 20 Hart, you know, and a couple different buses as standards now. To be determined if that remains, but appreciate the answer, guys. Dave Oler, did we take care of you there?
Yeah, I appreciate that. Thank you. I didn't want to be in a position where I'm specifying the wrong hardware for a DCS-based system versus a PLC-based system.
Nice. Okay. Thank you, Dave. I think we're coming up on 12:41, and thank you everybody for your patience. The pool is thinning. Oh, one just dropped off. We're down to 70 attendees now. I think we had a high of over 90 at one time. So we'll go to Mark Drocek, and this may be our last question. So Mark asked, how does the available pool of implementation firms impact the decision of which platform to use? And Mark, are you able to open your mic? Do you want to explain on that a little bit more? You're talking, you know, labor and available labor.
Integrators that are available to do the various platforms.
Sure. I think Charlie, we went to you first last time, so Grant, we'll flip back to you if you want to start us off, please.
Yeah, certainly. So how does the available pool of implementation firms impact the decision of which type of platform to use? So I would throw that back on you. I guess how important is to have that multiple vendors in terms to, you know, bid on a project to be competitive with the cost, having more levels, more people to go to, more firms to go to for support down the road. They say you're not happy with the initial supplier that put the system in. I mean, do you want to be stuck with them, or do you want to be able to go to somebody else? I'd say, how important is that to you?
And yeah, certainly, you know, the geographic location you're in. I've had experience working in the Midwest, and you know, there's the closest control systems integrator may be a 4 or 5 hour ride away, along with service technicians and things like that. So that's something you have to look at. You know, here in the Philadelphia or Baltimore, DC, there's always an integrator within a stone's throw from where your project is. Charlie, any thoughts on that? Available pool of integration implementation firms?
Yeah, I mean, that always becomes something we get evaluated when we're in a competitive bid situation where we have the technical support to support the plant. You know, so Siemens has a program we call a solution partner program where they're certified solution partners and we go out and train them. So the nice thing is there's no limit on how many of those we might need or have. We put them in strategic locations, so where we're strong. So we do have that pool of people, but obviously you go out in the middle of, you know, Montana for a system, we may not have a person out there within an airplane shot away. So it does become a conversation we have to have. So and it's important. Now, again, on the PLC side, normally, like even Grant said, while they're more customized, they're easier to, straightforward to work with and things like that. Whereas on the DCS side, you need to know that system better to be able to get in there and properly make adjustments or engineering. You can't just get somebody out of college and throw him out of DCS and have him, but we would argue that once he's learned, he'll be much more efficient configuring and programming a DCS than he would a PLC. So, hey, there's one question that somebody had though, and I don't want to get commercial, but they're asking me a question about the PCS NAO system. This, I can't read the person's name, Ishmael Beck. And if Ishmael's still online, we can have this offline, but the one thing I can tell you with the, we have a new system we launched about 4 years ago called PCS NAO. It's an extension of our traditional DCS. All the hardware is identical. So the controller and the IO, the servers, so the physical structure is the same. It's just a new software layer on top. So it modernizes our DCS for some additional functionality that we see coming into the future, i.e. ability to connect to the web, doing some things like that. So modular type package, I mentioned before, it's built for modular type package, so it's enhancing the technology to handle some of these new innovative type of systems that we see going out in the field.
Excellent. I'm Charlie, Grant, I'm putting your emails in the chat here. So I think we're going to conclude the formal portion of our awesome. Program today. And I want to say thank you again. This program will be recorded if you're monitoring the chat or looking at the chat. Once we have the program recorded, we'll upload it and we'll put the link here, so it'll be available for public download. We will put the actual video from today on YouTube, so that'll be available to the public at large. So we're how many people we got left? We have how many? 55. Looks like we got 63 total. So gentlemen, I think that sets a record for ISA Philadelphia for sure. And when we're working with ISA Baltimore, it probably I think you guys hold the record. So hold your heads high. Have a great weekend. We'll be sending you a coffee cup. Maybe we'll throw in a bag of Wawa coffee too. But I know you like that. So Charles, thank you again.
All right.
Grant, thank you again. Brian Ivy from Philadelphia. Lloyd Risser from Baltimore, Washington, D.C. Thanks so much. So I'm going to conclude the formal portion, and this may take a life beyond its own like a zombie. I think the chat may still be available, and then you've got the email for both our speakers today, so feel free to reach out to them. Thank you so much, everyone. Our next program is February 10th. We're talking industrial wireless in the 21st century. The link is in the chat to sign up for that. Have a great weekend. Thanks,
Awesome.
everybody.
Thank you very much, guys.
Everybody.
All right, take care.
Take care.
Thank
Have a
you.
good weekend.